So welcome to this Quintus Tech Talk. Today I'm interviewing Johannes Gårdstam from Quintus Technologies in Sweden. Johannes, can you tell me a little bit about yourself and what you're working with?
Well, I'm running the application center that we have here in Västerås with our HIP units and SIP units. And we have two HIP units, 121 and 19, and also a SIP unit that we can heat up, so it we call like a WIP unit. And WIP stands for warm isostatic press, SIP for cold isostatic press, and HIP for hot isostatic press.
Okay, and what kind of temperatures are you going up to, and what kind of pressures?
Well, for the HIP units, we go up to maximum 2000 degrees Celsius, and we use argon as a pressure media. And argon is a noble gas, so it will not react with anything actually in the press, the parts or the furnaces or the machine itself. But of course you can get some impurities into that also, but that will be more like a second question.
Okay. Yeah, and what about the SIP WIP? What kind of media are you using there?
For the SIP we use water or oil, and for the WIP we normally use oil, because that's if we go above the boiling temperature of water, for example.
Okay, and what kind of pressure are we talking about?
Well, around for the SIP units, like 5,000 to 6,000 bar, and for the HIP units, 2,000 bars.
Okay, interesting. So you mentioned impurities there. So I mean, what happens with the impurities in the HIP if they react with the parts? I mean,
what if you get like oxygen in your process? They will react and oxidize the part in most cases. It depends, of course, of what kind of parts that you have, but we try to get rid of those as good as possible.
So the larger HIP equipment that you have in the application center is quite sizable, but can the same machine handle different furnaces, or is it just one machine per furnace?
No, the same machine can use different furnaces. So we have three different ones. Two of them are made of molybdenum and can handle a temperature up to 1450 degrees Celsius. And one made of graphite, and that can go up to 2000 degrees Celsius.
Okay, and they're all running up to 2000 bar?
Yes.
Okay. Yeah.
Or actually 2070 bar.
Okay, 2070, yeah, 30,000 psi.
Exactly.
Okay, so that's nice. And so what are these different furnaces used for?
Well, the graphite furnace is mainly used for ceramics or refractory metals that requires very high temperature. And the two moly furnaces, depending on the cooling rate actually, because that's the difference between those two. One of them that we call the URQ furnace, uniform rapid quenching, have an included heat sink inside the vessel, so we can take the first thermal shock with a hot gas from the furnace and just put it into the heat sink, and take the gas from the heat sink and put it into the furnace. So then we can cool the gas actually with 30,000 degrees per minute.
Kelvin per minute?
Kelvin, yeah.
Wow, that's pretty fast.
Yeah, so it's just one or two compressor strokes to get it down to 100 degrees.
Wow. So what kind of metals are using that kind of furnace?
Low alloy steels require very high cooling rates. Aluminum, if you want to perform a T6 treatment, requires also very high cooling rates. Some nickel-based super alloys can require that as well.
Okay, yeah, okay. And then the other furnace you haven't mentioned yet, the URC furnace, what's that, the uniform rapid cooling?
Yes, that uses the whole space in the vessel that you can use as a hot zone for your parts. And the cooling rate is a little bit slower compared to the URQ. We can end up with between 200 and 300 degrees per minute in that one, but actually that's the workhorse for us. We run around 60 to 70% of all our cycles in that furnace.
Okay, and the cooling rate to 200 to 300 Kelvin per minute, I mean, can you steer that in any way, or is it just free fall?
Yeah, that's also one of the benefits with that furnace, that you can steer the cooling sequence. Actually, you have 6 thermocouples in the furnace, and you can use one of them or all of them or just a part of them to control with. So you can set that cooling temperature actually between 0 to 300 degrees, and what you want actually in the gas. Or if you take one of the thermocouple and put inside a part and you can steer with that, you can actually control the cooling rate of that part instead.
Okay, so you can actually measure the temperature inside a part.
Yeah, if you put a thermocouple inside a part, you can do that.
Does that give opportunities then for modeling this, or to have a look at how parts behave in the hip?
Because the gas, the high pressure gas that we use, that circulate with natural convection during the heating sequence, and also the soak time. But during the cooling sequence, we have a forced gas flow. But since you don't have any boiling or other complicated features that appear compared to when we have a liquid or as a quench media, it's very easy to calculate and know how this will behave, the relation between the gas and the component, and how the heat exchange how that will work actually.
Okay, and do you see a difference then at different pressures as well? I mean, do you see any changes in the cooling rates based on pressure?
The connection or the heat transfer coefficient increases with the pressure, or actually the density of the gas.
Okay.
So we will not reach like water in heat transfer coefficient, but it's much better than like normal atmospheric pressure air. So it's very similar to high pressure gas quenching.
Okay, that's interesting. So you can actually steer the cooling rate. You know what you can model what's going to happen with the parts based on a CAD drawing, I guess.
Yes.
Yeah, and then you can predict pretty much what the microstructure will be inside the material then.
Yes.
All right, that's very interesting. So this is combining then both HIP and heat treatment in one step.
Yeah, that's one of like the benefits with this, that you don't have to heat up the component and do multiple different units of treatments after each other. So you can combine a lot of these in one machine.
Okay, cool. So this, I know Quintus call it high pressure heat treatment. You're doing lots of different steps here. So what kind of materials are you doing solutionizing steps on?
Well, mainly it's on nickel-based superalloys. That's require a solutionizing step, but actually that only require a specific cooling rate or above a specific cooling rate when the parts have been above a certain temperature. Okay. And since the HIP temperature is above that, and if we can cool with a sufficient cooling rate, we can combine the HIP and the solutionizing step.
Okay, can you steer stepwise the cooling rate as well, so we can stop at plateaus?
Yes,
of
course. Yeah. Since we cool the media, we are not like put the samples into a cool bath, for example. We cool the media at the same time, so that's also will be very beneficial for the components. You will not get high stresses or large deformation because you have less thermal shock to the material.
Okay, interesting. So being able to take a stepwise cooling profile, if you like. Can you do the same with heating, by the way? I mean, can you do the heating profiles upwards as well for specific materials?
If it's required, yes, of course. It's pretty easy to program.
Okay,
and you can go up with pressure first, and you can heat it later.
Okay. Yeah. So all these trials are possible then in the unit. Right. Okay. Cool. So I mean, on the cooling side, I mean, are you also doing aging in the HIP after the solutionizing steps?
Yeah, of course it's possible to perform aging because you can heat the furnace, and if you require a certain temperature for a certain time, you can leave the parts in the furnace.
So you can actually do quench and tempering as well, I guess, in stepwise up and down. Yeah.
That's
okay.
Also.
Very interesting. Yeah. So you mentioned earlier about the cleanliness of the gas.
Yeah.
I mean, do you see the work you've been doing now on trying to keep the environment clean? Can you see the effects on the parts as they come out of the HIP compared with the way you used to do it?
Yes, we see a big difference because we know what causes the impurities or the reactions and how to get rid of it. Of course, there are materials that are extremely difficult to get clean because they have some alloying elements that, like sucking oxygen and want to create oxides. But most of the material, I should say, whether it's critical with clean surfaces, we can manage.
Okay, and so how do you know? And you're looking at the chemical composition of the gas. I mean, how are you measuring that? How's that being set up?
Yeah, well, in our application center, we have a gas chromatograph, and we also have moisture sensor and oxygen sensors. And we, as the only lab that I'm aware of, we can extract gas from the hot zone, so we actually see when reactions happen in the hot zone volume. So we can follow the reactions. So from the beginning, if we put in like pure argon, we can see how like some moisture can be released when we heat it up, and how the moisture will react with the parts, when hydrogen will be created, since the moisture will react with the parts, for example.
Okay. So you've been doing a lot of chemistry then as well,
yeah,
at high temperature.
Yeah.
Yeah. Okay, nice. So based on this, then you've got different furnaces for different materials.
Yeah.
You can do the steered cooling,
Yeah.
very clean cycles.
Yes.
I mean, what's next?
Well, one next step, I should say, is that we could maybe add active gases, so we can also like produce an extra step, like case hardening, for example, could be one extra step. We can add a sintering step in the beginning, so we can combine even more cycles or heat treatment methods in one cycle.
So apart from the Quintus Application Center in Västerås, what other application centers are there out there in the world?
Yeah, we have one in Columbus, Ohio, in the States, where they have a 15L, a slightly smaller machine compared to the 21 that we have here in Västerås. And they also have a sip and whip equipment. Then we have in newly opened application center in Takasago in Japan, and where they have a 21, similar machine as we have here.
Right, and both of those machines have the opportunity to have the 3 different furnaces as well?
Yes, they have both URQ, URC and graphite furnaces.
Okay, so they can support basically the industry globally now. Yeah,
yeah, I should say so.
Yeah, so how many projects do you think Quintus is working on with the different institutes, universities and customers today?
Well, I haven't counted them, but I should guess between 50 to 100.
Right.
Because we are involved in a lot of research projects, especially connected to the AM, the additive manufacturing industry. There's a lot of focus on that right now, and how HIP could help when they like hits, when they struggles with the quality of the components. How can HIP be a part of that?
Okay, so I mean, just quickly on that then, I mean, on the additive manufacturing microstructures, I mean,
yeah.
what are the challenges? I guess there's some porosity and some issues there.
Yes, yeah, well, they have porosities and they have like lack of fusion and only micro cracks inside. And if HIP can heal those internal defects, then of course it's beneficial.
Yeah. So you see a change in which alloys are coming into the shop now from out there?
Yeah, I should say so, because in the past we run a lot of like titanium 6.4 and a lot of Inconel 718. We still do that, but we are now struggling with more like complicated materials where the additive manufacturing industry have not worked with for like decades, so they're more new for them as well, so they have more defects inside. So especially some non-weldable nickel-based superalloys are more common today.
Exciting. So Johannes, thanks a lot for taking the time today to come and talk to us. And if you're out there watching, Quintus can help you with your applications, your development of your materials, and of course any university projects that you're involved with as well. So if you're out there doing R&D work, or if you're looking at actual mass production, of course we're here to help. So take the chance to look us up on the web, send in information to us, and we'll help you as best we can. So thanks for tuning in, and keep an eye on the tech talks that are on the web right now.